Now this video also, if I have time tonight, or I'll do it first thing tomorrow morning, I'll post it online. Couple of announcements about this week. Wednesday. Now there is the big review session, which is 9:30 to 11:30, and unless I figure out a better place in another building, it will be 9:30 to 11:30 in Lamar. It works really well, and I think it's late enough that I don't have to worry about people interfering with what's going on. But earlier today, or in the day tomorrow, at 9 a.m. to 10 a.m., I'm doing I have office hours. And if you want to meet then, it will be in the conference room of Weir. This is the one in the computing room, or the computing lab. So I'll be available tomorrow. If you drop by, if you're the only person there, it's $20. If you're if you're one of 10, it's still 20. It's kind of like a mini review like we did tonight. Now, then that's all we got. The test is Thursday, so that's it. If you want to meet or contact me, I'm either at Twitter handle of Dr. V, and if you on Facebook, I'm at Eschenberg Education, and so then you can contact me through there. And then my email address is drv@eschenbergeducation.com. So I have business cards if you want to pick that up, and you can contact me later. We have about 5 weeks before, or no, we're down to 4 weeks before the final. Not much time, but I'm here to help. Let's get to it. Earlier today, I was talking with a few of the other students, and one of my weaknesses as a professor was that if you were going to figure out what was on the test, I was telling you during those lectures leading up to the test. Because what I was doing was going over potential problems, testing them out. If the students liked what they saw, I would put it in. If they seemed totally confused about it, I would get rid of it. So in the end, everything seemed to work out okay. My guess is there will be 8 multiple choice. 8 to 10. Just like there was on test 2. As for the specifics of it, I found that when I gave the multiple choice, and I think I'm of the same opinion as him, that it's a test of depth of knowledge. Like, how well did that information penetrate your skull? And if you get it really well. Now, one of the things that I did was that my multiple choice, I had 25 2-pointers. He's got 8 to 10 5-pointers. So there's a little bit more at stake when you answer a question. But the big 4 problems, from what I understand, he's now developing his routine. The first test that he ever gave, he was making procedural mistakes, and then now he's starting to fine-tune things. I think there will be the 4 problems where the maximum grade that you can get is 120 out of 100, and these will be the 4 types of problems. I think it will be circular motion, which is chapter 8. I mean, this is no big deal, but we're gonna work on this. There is rotational and translational equilibrium. I think there will definitely be one on fluids, and then basically pendulums. Now, it's no big surprise. What he's going to do is he's going to have a problem, one out of chapter 8, one out of chapter 9, one out of 10, and one out of 11. I think that these three are semi-predictable, more predictable than others. I think what I tended to tell my students was that fluids was the wild card of the thing, because there's just so many problems that you can ask about fluids that it can come from all sorts of places. So what I'm going to do is, for the initial hour, spend about 15 minutes each on circular motion, rotational, translational, equilibrium, fluids, and the show. And then for the last 50 minutes or so, or a little bit more, we'll go over specific problems. I'll answer questions from the room, and we'll just go on from there. All right. And let me make sure. Oh wow, this is a wide. I can do all sorts of fun things with this. All right, now for circular motion. You're all familiar with X, V, and A. The position, the velocity, and the acceleration, where velocity is the change in X, and A is the change in velocity. In rotational motion, the big three are theta, omega, and alpha, where omega is the change in theta and alpha is the change in omega. And in rotational motion, we're talking about similar to circular motion, where in a circular motion, if you have a V that over a period of time changes, this implies that there is a radial acceleration that is perpendicular to velocity and always points inward. So if you have a thing that's rotating in motion, if V exists, there is a radial acceleration. And that the relationship between the two is AR equals V squared over R. That the radial acceleration is this. Now, circular motion and rotational motion have the same things. We're all familiar with what I call Dr. Eschenberg's favorite equation. It exists in the rotational way, that there is theta and angular velocity. I believe from what I hear, he is what I would call radian friendly. The angle is just an arc. Technically, there are no units. If you use, in the case of omega, radians per second, I don't think he is overly sensitive to it. Technically, it's supposed to be that. But I'm a little upset about using spaces and mentioning units that doesn't have a unit in it. But I think he's fine with it. So I think this is perfectly okay, and I think that is perfectly okay for the units of that. Yes?
Okay, on his equation sheet, he doesn't have the theta before the omega.
Now, in 99.99% of all cases, that theta is equal to 0.
Okay.
that the initial position is 0.
Okay.
If he mentions from rest, that omega naught is 0. So I just keep it there. It's basically the appendix of values. Yes?
Can you specify what's in that circle? I can't really see it.
You mean this right here?
Yeah, I think it's
Okay.
AR with arrows, right?
Yeah.
Okay, yeah. Thank you.
That is. So what happens is that you've got, that is the radial acceleration vector pointing inwards. That's the same thing. Those are velocity vectors, and it's at right angles.
Got it.
This is why I love Elmos, because you can go, what is that? And then I can zoom up on it. I just need to remember to zoom back out. That's my problem.
So I have a question. Like in linear acceleration and velocity, would you say that if the radial velocity is constant, would that mean that radial acceleration is 0?
Let's talk about that. That's a good idea. This is, I have a problem that I call, not my personal problem, it's a physics problem. I call it fish of fury. Fish of fury grabs the bait and it travels at 15 meters per second. So the spool, 15 feet per second, is constantly coming off the spool. Now, that means that it's rotating. Is it rotating at a constant rate? Yeah, it's rotating at a constant rate. The equation that we use is V equals omega r. That at a particular angular velocity, at a particular radius, it's moving at 15 meters per second. Now, if it's moving at a constant 15 meters per second, what is its angular acceleration? If it's just constantly rotating, minding its own business, what is its angular acceleration? It's 0. Because if it was non-zero, it would either start slow and speed up, or start and slow down. Now the last bit, the radial acceleration, what is the radial acceleration based on? The velocity at the edge. If the thing is moving, that point is accelerating inward, which means that a moving point implies that radial acceleration is non-zero. So it does exist. And it's non-zero. If it isn't moving, it would be 0. And that brings up some interesting points, that alpha is omega r, and that's not that. Alpha is AR and omega is BR. And that particular A is linear acceleration, not radial acceleration. Radial acceleration and linear acceleration are two different things. They represent two different qualities about the stuff. Now, there are other things that we need to keep understand, is that mass goes to I, moment of inertia. And that P goes to L, which is angular momentum. And force goes to torque. And that symbol there is a Greek T, or tau. So there are a lot of parallels between these two. And one of the great things that I do for circular motion is with this, you have in linear terms, it's F equals ma, or the sum of the forces is equal to ma. In rotational, its torque is equal to Fr, but you can also say that the sum of the torques is equal to I alpha. So the torque is the force times the distance, and what we do is we choose our rotation point. We have our lever arm, which is our R, and then we have this, the F that is perpendicular, the force that is perpendicular to R. Simple example. If you have that rotation point and you have that force at an angle, and that theta is 60 degrees and F is 100 newtons, and R is 2 meters, tau is equal to that F that's perpendicular times R. And what is that perpendicular force? Well, that's F perpendicular, and that's F parallel, which we could say is Fx and Fy, and that's theta, and that's F. Having a knowledge of trig means that the cosine of theta is adjacent over hypotenuse, which means that F perpendicular divided by F, or F perpendicular, is F cosine theta. So this is F cosine theta times R, so 100 cosine of 60 times 2, or 100 Newton meters. And Newton meter is the unit of torque. For torque, we use Newton meter. For energy, we can use either Newton meter or joule. So in this particular problem, what we're going to do is we're going to use a disc. And what I want to do is a simple rotational motion problem. If force is equal to 100 newtons and the lever arm is a radius of 2 meters and the disc is 50 kilograms, how many times does it take to rotate 200 times? In this, what we're going to do is we're going to demonstrate general problem solving. Oh, and it goes from rest. So how many times did it take? In linear motion, when you're doing 1D or 2D motion, there is a very set way of doing things in terms of you have to establish your origin, blah, blah, blah. Very straightforward. I equate solving rotational motion problems kind of like looking at a situation, taking your toolkit out and rummaging through it. Whereas in linear motion, you may have 2 or 3 equations. In rotational motion, you could have as many as 10. But if you know what 10 you got to use, you can start developing an instinct on how to work with this. The equations that you need are theta equals, and I'll write this the way that he does, omega naught t plus 1/2 alpha t squared. Torque is the force times the distance. The sum of the torques is equal to I alpha. Couple more equations that you need to know is theta equals 2 pi n. That's another guy that's really important. Theta is that theta, the arc, and n is the number of rotations. So in this particular case, what we start doing is swapping things out. What was I given? I was given the number of rotations. So I can eliminate theta with 2 pi n. I can also say it's from rest, so that goes to 0. And I'm left with 2 pi n is equal to 1/2 alpha t squared. Now I know what n is. I'm looking for t, but I don't know what alpha is. So much of what rotational motion is about substitution. Well, what are we substituting in? The sum of the torques is I alpha, so the one torque is equal to I alpha. I, the moment of inertia of a disk, he's going to give you that. He's going to tell you, he's on the equation sheet, and it is 1/2 md r squared. And tau is Fr. So Fr is equal to 1/2 mdr squared. What I'm going to do, and then alpha. What I'm going to do is solve for alpha. This r is little r, so one of those cancels, and alpha is 2f over mdr. So all I did here was tau becomes Fr, I becomes 1/2 mr squared, the alpha comes down, and one of the r's cancels. So this becomes 2 pi n equals 1/2 2f over mdr t squared. My 2's cancel. I'm looking for t, so this is 2 pi n mdr over f is equal to t squared, or t is the square root of 2 pi n mdr over f. This is 2 pi 200, md is 50, r is 2, f is 100. So that will cancel, leaving a 2, 100, 400, 400 pi, square root of 400 pi, which is 20 times the square root of pi. So it's roughly like 35 or something, I think. Where's my cat? Oh, there you are. So let me do this outright. 2 pi times and I get 35.4 seconds. And so that's the total time that it took to accelerate. Now, one of the things that I believe in passionately is the alphabet soup model of doing things, where everything is done with equations in the last moment. Because if you have something rotating and you need something described in terms of the mass, the radius, the number of rotations, the force, the time. This is the foundation stone of the problem. I could have asked for the number of rotations, the force, the time, the mass, the radius, all from that one equation. If you could set it up to that, you're able to solve for anything he throws at you. And so what I'm trying to do is teach the general problem solving skills so that you can take and solve anything. So for rotational motion, this is the kind of thing that goes on. And what I want to do is I want to start moving through the other bits of material and that we can cover those. Now the next thing that I want to cover in this is rotational and translational equilibrium. Now, a lot of you think your parents tell you you're not doing anything. You could tell them, or you're just lying in bed doing nothing, and they go, well, you're not doing anything. And you can turn to them and say, honestly, Mom, I'm studying physics. Because if you're not doing anything, like this water bottle on the table, what do I know about the water bottle? It's not doing anything. Not doing anything means oh so much. Not doing anything means that it's not moving up or down. And it's not rotating. If it's not moving up or down and it's not rotating, that means there are two equations that are your friends. That the sum of the forces most often in the vertical is 0. The not rotating means that the sum of the torques is equal to 0. Those two equations are your best friends when it comes to. Now, the problem that a lot of people do is like a torque bar problem. And so a common torque bar problem that works with this, and doing a problem is probably the best way to demonstrate this thing, is you have the string at the end of a pole. And you have the normal force from the fulcrum onto the pole. Pole's massless in this case, just to simplify things. You have a 50 kilogram mass at the end. And what I want to know is if x1 is equal to 2 meters, bless you, and x2 is equal to 1 meter, what are the forces F, normal, and tension? This is a classic rotational equilibrium, a classic translational equilibrium, and all sorts of varieties of this can be on the test. And so I'm going to do this, and I'm going to teach you why he does. Some of the students have seen this weird hand gesture that he does, that for experienced individuals, it means that he's working through something with his right hand very quickly, and we'll see what it means. If it's when you see a problem like this, you attack that problem first and that problem second. The reason why you do torque like this is that there are two wisely chosen rotation points, A and B. There was a top hat question that he posed in class where you saw something similar to this, and there were weird arrows all over the place. And these people are seeing. And he asks you the question. Let me explain what he was asking and be the devil's advocate, or devil's well-spoken advocate. What he was trying to do is get you to figure out what spot would eliminate those unknowns that you don't know at the moment so that you don't have to play with them. I can't sum the vertical forces here because I know this force, but I don't know those two. Those forces are unknown. The best way that I can do this problem is to choose a rotation point wisely such that torque is the force times that distance, r. Well, if r is 0, the force could be infinite. Infinite times 0 is still 0. Or very big times 0 is definitely 0. So what we want to do is we want to choose a rotation point either there or there such that if I choose A, Fn does not contribute. If I choose B, T does not contribute to the sum of the torques about that point. And what we're going to do is we're going to solve for one of these forces and then switch to that one and sum the forces there. So I'm going to pick A. Why A? I don't know. I just typically pick the leftmost. This means that that is 0 for the first torque. The sum of the torques is 0, but the force torque from Fn, well, that's 0 because the radius is 0. I normally don't write that 0 down. The next force is mg because it is acting with gravity. And then its distance is from there to there, or x1. Now, tension is the force for the last torque. Its distance is x1 plus x2. The distance from the rotation point to the force itself is the sum of the distances. Now, if the total distance was given, you would just write that down. But since they were listed as parts, you got to do this. Now, what I'm going to do is this. And I'm going to show you why that works that way. And that is, I have to introduce to you something that's called the right-hand rule. And the right-hand rule involves two vectors with that symbol. That is not a multiplication symbol. That is what we call a cross product symbol. And that is equal to the third vector. Now, the motion that he does, he's at the board, so he's kind of at the board with his back to the audience. You see him do that, this weird, like, twist motion on his hand. The motion that I want you guys to know is this. This is greatly exaggerated. I don't normally do this when I'm working because mine looks very simplified. It is this, 2, 3. I'll do it again. 1, 2, 3. Or 1, 2, 3. So there are 3 particular motions. Oh, you see wisdom being presented. So the first vector, what do you notice? I've been working with my niece since she was 3. She was in a no phase between 3 and 6 and refused to do it. Finally, when she was 8, she did the hand gesture. Hey, you've taken the class. What are you doing here? Okay. So what this is, the first vector, fingers, palm, and forearm all align in that direction. The second vector is fingers only curl. in the second direction. And then the thumb naturally extends in the third. Now, with torque bar problems like this, you're only going to have one of two different things. It's either going to go into the page where the symbol looks like that, or out of page where the symbol looks like that. And the difference that you can see is, wouldn't happen to have a meter stick on it. So if I have my little magic, since the people over here probably haven't seen it, if I have my little magic bow and arrow, and I take my magic bow and arrow and I have it aimed at the face, what do you see? You see the business end of the arrow. That's the tip of the arrow. That's the vector coming out of the board at you, which is the one on the right, the circled up. Well, what if you had your magic bow and arrow and you were aiming at me? That's the arrow going into the page. What do you see at the end of the arrow? The flashing. So that's the arrow going into the page. Now, if it's into the page, I'm giving you like the 5-cent tour of right-hand rule, not the half-hour special that he got. In the end of the page, that represents negative. And if it's out of the page, that's positive. So in cases like this, where the R is to the left, I chose A, hold on. So A is the rotation point. Always start at rotation point. The R is to the right, and then F is in that direction. Oh, dang it, hold on. I'm doing this. M is down. And then A again, and then T is up. So those are the two vectors. Now let me blow, what I want to do is I want to blow this up so that we can see it. All right. Now what I'm going to do is I'm going to hold my hand up to the screen. In both cases, you always start at A. So A, R, for both of these is to the right. So the first vector is like this. And then the fingers point down. That's the second vector, because in A and M, or MG it should be, that vector is pointed towards the floor. And where is the thumb naturally pointing? Now the thing that you need to remember, Shanterica, is it's called the right hand rule. What hand are you using? Your left, exactly. Don't make fun. Only I can make fun. So, but I can guarantee you that someone else in the room is using those hands. See? Wasn't the only one. You two can beat him up later. So, the second vector points towards the floor. The thumb points into the page, or into the screen, so that has to be negative. A to T, or R to T, R is to the right. Now, T is up, and I can't bend my fingers that way. So what I do is I rotate my whole forearm over. Now, it's still aligned to the right on the screen. So when I go T up, the thumb points out. That's positive. Yes. As long as, see, this is allowed, that's allowed, that's allowed. Because in all three cases, the forearm, palm, and fingers are still headed that direction.
Okay, so for the first one, did you test for rotated, or the one that you don't rotate?
No, because when you do the force has to be aimed down. That's the right way to do it. Okay. So for the one one with the M, which should be mg. And I'll do it here. So R is in that direction. Force is down on the page, so if you're looking down on your page, the thumb is hitting the paper. That means that the torque is into the page, and it's negative. Now, in a problem like what we're studying, it doesn't really matter, because as long as you know they're opposing each other, flip the signs and it still works the same way. It's when you have multiple torques running around at the same time, like 3 or 4 or 5. It really helps. And then this guy, the force is to the right, the tension is to the top of the page, so the thumb goes out. And what I would do is, if you talk to, we still got tomorrow and then all of Thursday. Talk to Dan Miller or John Rock or Michael Giandrin. Get them to teach you the subtle points of the right-hand rule. Just the quick and dirty way to do the torques on the torque bar. Because really, for something like this, we shouldn't be spending like 15 minutes on this. But it's good to get out. So to the right, mg is down, thumb heads into the board or negative. For tension, it's to the right, but up, thumb goes out. So that's out of the board or positive. And so that's the right-hand rule in that shape. So let's look at this particular problem. So we've assigned the negative signs. And, excuse me? Oh, zoom out. Thank you. I forget that so often. All right. So those forces are added up. I'm looking for T. And now I've got it. So this is 59.8, 2 over 2 plus 1. 100 times 9.8. And I get 326.67 newtons. And that is the tension in the string. Yes? The what direction? Oh, because this is F times R. R is the distance from A to the force. What's the distance from A to the force? 0. So that's why I can ignore it. Had I chosen B, R would be x1 plus x2 for that F. And then the R for the tension would then be 0. So this is where that whole thing with this is him trying to show you why that's 0. Because it eliminates unknowns and helps. Now that you have the tension, the quickest way to do this is to use your best friend. Sum of the vertical forces is 0. And it's obvious what the signs are. Up is positive, down is negative. So now, what am I looking for? mg that comes over is equal to Fn. So, Fn is mg minus t, m is 50, g is 9.8, minus 326.67. And I get 163 and a third Newton. And so that is the vertical force pushing up on the bar. And so chapter 9, with time, and what we're going to do is with time, we'll do more examples today and tomorrow. We'll study more torque bar problems. And I really think the one that if you look at it and you can figure it out, the one that we'll do eventually. And if you don't know me, for the last 5 years, I recorded almost every single lecture and tutorial that I've ever done for Physics 213 and 214. So what you want to do is, on YouTube, there are videos that have the word tutorial in them. And I believe there's even a test 3 review. What you want to do is you want to look at those tutorials and look for, when I'm talking about problem sets 6, 7, and 8, I believe, maybe 9 for the last chapter. And so those tutorials, all I did 2 hours a week, well, no, hour for 213 and hour 214. I would sit down and do problems. So if you look at those videos, find them and you can watch them and then you can pause it and go back and forth. And I even do a lecture on the right-hand rule and how it works. And so you can go back and search through it and see it. The next thing that I'm going to do is fluids. And fluids has its own little thing about what to cover. I call this the Swiss Army knife of equations. And why is that? Swiss Army knives are oh so useful. What I would do is I would know that this, that, and that are all very handy equations that if you don't know something, either mass, volume, or density, plug in one of those things and eliminate it. So it's a very handy thing. Now to just review fluids real quick. Pressure is rho g h, where this is the density of the material and that is the height. It doesn't matter if the base is a square or a wide ellipse or a circle or a pentagon or a pentagram. As long as you have the height, you can figure out the pressure at the bottom. The total pressure at the bottom is the pressure from the object plus 1 atmosphere. That if you have a particular pressure from the object, you add 1 atmosphere, because if you have a mass like this, there's all that air on top of it pressing down. So you have to add 1 atmosphere of total pressure to the thing. This is similar to gauge pressure because gauge pressure plus 1 atmosphere is total pressure. The gauge, with your air pressure gauge, when you put it on a tire, it's not telling you the total pressure of the tire, it's telling you the pressure above atmosphere. So had you let's say you theoretically you open the tire up so that it's exposed to the air on the outside and it goes whoosh. You put the air pressure gauge on the tire, it's gonna read 0. Why? Because there's no additional pressure in the tire pushing back on the on your pressure gauge. So you need to know what that is. There is Pascal's principle. I can't spell Pascal. You're going to have to look that up. So Pascal's principle, I think it ends with an E. It's L, just L? Okay. In my class, I don't take off points for spelling errors. For Pascal's principle, that the pressure of 1 is equal to the pressure of 2 if the depths are the same. So if you have a pool of water and you have a point there and you have a point there and you fill the tub with water, that the pressure 1 is equal to the pressure 2. That the pressure experienced on the bottom is the same as the pressure experienced, or left bottom is the same as it's on the right bottom. Now what I can do is I can start slicing out the water. So now it's only this tube right here. Where's my blue marker? There we go. So if this is in blue, so that's water, and I filled the rest in with dirt, that it's still at the same depth, so that it's still at the same pressure. The other thing that you can know is that the pressure there is the same as well, 3 and 4. So pressure 1 is equal to 2, pressure 3 is equal to 4, because 3 and 4 are at the same depth. And it's very useful for situations such as your brakes, your brake pads. You may have heard a mechanic talking about a master cylinder. The cylinder is filled with hydraulic fluid. So you push on your brake pedal with a force of 100 newtons, and the area is 2 square centimeters. And further down the line are your brake pads. Let's say that's a brake pad, I don't know. So the area of your brake pads is 200 square centimeters. I don't know what the area of a brake pad is, but it's going to prove the point. What's the force that's applied on the brake pads? So what we have here is A1 F1, or I'm sorry, the pressure of 1 is equal to the pressure of 2. Well, what is pressure? Finally, we get to talk about it. Pressure is the force divided by the area. So pressure 1 is F1 divided by A1. And F2 is divided by A2. So solving for F2, F2 is A2 F1 over A1. A2 is 200. F1 is 100. A1 is 2. So the force that we get out of this is 10,000 newtons. So from a simple 100 Newton force, we can get a lot more force on the other end. Now, one of the things that I do stress on is that you guys need to use the appropriate units. And one of the things that I did is I did not plug in square meters for that point right there. Why did I not plug in square meters? Is centimeters squared and centimeters squared will cancel. It's an unnecessary conversion. Had you converted to meters squared, you'd get the same ratio, and that's all that you really need. You don't need to use square centimeter or square meters in that case. For pressure, you do have to use newtons. And so then we get 10,000 newtons. Now, the thing that we need to pay attention to, among all sorts of things, a couple of the students, yes?
I just had a question about pressure. So pressure can equal rho times gravity times height and force or area?
Yes.
That's how it is.
Yeah, because, and there is a derivation where really you start with this and you end up with that. So it's a shortcut. There's a proof to it, but I'm not going to go. If we want, I can talk about it later. Now the units from F equals, pressure is F over A. F is a Newton, A is a meter squared. Now, 1 Newton per meter squared is a Pascal. The other thing that people seem to be like, well, where did he pull this from? And I think it's very critical when we continue on with fluids, is that 1 atmosphere is 1.013 times 10 to the 5th newtons per meter squared. He was throwing around a bunch of 10 to the 5ths all over the board, and a lot of people were going, well, where is this coming from? It comes from here. It's a unit conversion from newtons per meter squared to atmospheres. All right. So we got to know about units. So what do we do now? All right. We're going to do buoyant force. Probably spend about 10-15 minutes more on fluids, 5 minutes on oscillators, and then we'll start just throwing out problems. With the buoyant force, this is FB is the buoyant force, G is the gravity. Rho sub D is the density of fluid displaced. And VD is the volume of fluid displaced. And so those are what the D's are. If object is submerged, meaning it's completely underneath the surface, the volume displaced is equal to the total volume. Excuse me. Now, for something like this, what I'll do is just demonstrate it from a simple example. You have water covering let's say it's a hollow shell, so there's nothing in it. But the mass of the shell is 400 kilograms. Now, it's tied to the bottom, and the tension of the string is 20,000 newtons. The question that I have is, if the density of water is 1,000 kilograms per cubic meter, what's the volume of the sphere? Now, it's tied to the bottom, which means it's not doing anything. Yay, not doing anything. Which means that the sum of the vertical forces is equal to 0. It is in translational equilibrium. Now, the forces that we're dealing with, and it always helps to have a force diagram on this. Because it's underwater, there is a buoyant force up. There is a tension pulling down. The shell does have mass, so it's an MSG. Let's list the forces. Buoyant force up, tension down, and MSG down as well. I'm looking for volume, and I don't see volume in here. Well, let me tell you where it comes from. The buoyant force is rho Vg. So 0 equals rho Vg. This rho is the density of water. Since it's submerged, I'm not going to use V sub d, I'm going to use V, and then there's gravity. There's tension, there's the mass of the shell times gravity, and that's it. Now all I got to do is solve for V. T plus MSG is equal to rho WVG. And that means T plus MSG divided by rho WG is equal to volume. So T is 20,000. Mass of the shell, 400. Gravity, 9.8. Rho water, 1,000. And then gravity is 9.8 again. Which means that the total volume of this thing is 2.44 cubic meters. And so this is just a simple application of buoyant force and translational equilibrium. And we'll get more complex as it proceeds. The moving on to other parts of the fluids, is there has to be, I won't go into the full detail of the thing, but there is the terms called neutrally buoyant and that just means that the sum of the forces in y is equal to 0 and its motion is side to side. There is negatively buoyant where the sum of the forces in y is less than 0 and it comes down, and there is positively buoyant where the sum of the forces in y is greater than 0. And so those are three rather big definitions that are very good for multiple choice questions. Though his multiple choice tends to be kind of smallish problems. Now, my, equation of continuity. Oh, but first, hold on, let me write this down and then I gotta do something. Let me tell you one of my favorite, if I did Top Hat, which I don't, I only use it for attendance. But let me ask a question over here. And if you know it, because I told you, don't tell the others. So you have an ocean. And this is something that creeps up on, let me know if you've seen it, because the TAs may ask it, since this week is Archimedes' principle? Is that what it is? Okay. So you have two objects. Object 1 has 1 cubic meter. The object on the right is 1 cubic meter. They're both in water. The density of one is 2,000 kilograms per cubic meter. The one on the right has a density of 3,000 kilograms per cubic meter. The question, I know who I've talked to and who I haven't, so I'm going to be coming over here. The question is, which one has the greater buoyant force and is displaying yourself? Why? Oh, you started so well. Don't fade. I'm actually more offended that you're not showing the confidence that I want.
I mean, I'm saying like, I'm pretty much feeling that I always say buoyant force is gonna act as a plane.
Well, they're both resting on the bottom. I can
Yeah.
see that.
So, I
But
mean,
the buoyant force, what is the buoyant force?
it's the force equal to the weight of the water vessel. Well, yeah, that.
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 I think what you were talking about was the normal force. The normal force would be different.
Okay.
But let's talk about what the buoyant force is. What's the first symbol? It's rho of what? The fluid being displaced. Are they both displaced in water? Yes. Second symbol. What does the second symbol represent?
Velocity.
Now you can laugh at him all you want. It's the volume of the fluid displaced. So the volume of displaced is the same because they were specifically stated to be 1 cubic meter each.
Yes.
They're both on, well, they're both on the ground, but the buoyant force doesn't care about it resting or not. What it does care about is gravity as the third quantity, and they're both experiencing Earth's gravity. So they both have the same fluid displaced, they both have the same volume displaced, they both have the same gravity, so they both have the same buoyant force. The density of the material is irrelevant. And so that's the big reason. And yes, I have said velocity myself.
Sorry, I just got out of that laugh.
But it may be, see, all the TAs pull their quiz and exam questions, maybe not all. The new ones pull them out of a bank of multiple choice questions, which oddly enough came from my tests, and that one creeps up a lot. Michael asked that one? Okay.
He asked for my brother too.
Oh, nice. Oh, yeah. Well, that's good. So the equation of continuity is that. I also call it the conservation of flow. What this is the flow rate of fluid coming into a pipe. That's the flow rate of fluid coming out of the pipe. The amount of water coming into a pipe has to be the same as the amount coming out. You just can't have fluid magically appear or disappear. So the two big examples are cover half of a garden hose with your finger. And this means that A2 is equal to A1 divided by 2. Now what this means is A1 V1 is equal to A1 over 2 V2. Which means your new velocity is twice that of the old velocity. And it makes sense. If you cover your thumb over the half the hose, that water still has to come out. So what it does is it shoots out more quickly. Another example, if you turn on your water faucet and just let it kind of flow out, not a trickle, but not a torrent, what you'll notice is as it falls, it gets more narrow. The A1 V1 at the top is constant because it's a constant flow rate, the water coming out of the pipe. But as it falls, V2 increases. And if A1 V1, which is a constant, equals A2 V2, if V2 increases, A2 must decrease. And so that explains equation of continuity in two very simple examples. Now the big guy, among the last things for fluids before we get into oscillators, is Bernoulli's equation. And what I'm going to do is, there's examples online of me talking about the shower curtain, but what I want to do is a more appropriate equation, which is that Bernoulli's equation is P1 plus rho G H1 plus 1/2 rho V2 squared. I'm sorry, 1 P2 plus rho GH2 plus 1/2 rho V2 squared. And that is my least favorite equation because it's so dang long. Now for something like this, the problem will be is that you have a hill where H is 20 meters high. That the velocity is at the top equal to 4 meters per second. The area of the pipe at the top is 20 square centimeters. At the bottom, trying to make this interesting. At the bottom, the area at the bottom is 10 square centimeters. The two questions that I have is, what's the pressure at the bottom? If the pressure one at the top is 3 atmospheres, and what is the velocity at the bottom for something like